What up YouTube? In this video I'm going to show off an inductive guided robot that I made a couple years back. For those of you who don't know, inductive guidance or wire guidance is a technology that's used mostly in the warehouse industry for autonomous guided vehicles or automated forklifts. It is a system that allows a vehicle or robot to navigate through an area without a physical track. Instead of a physical track, there's a wire embedded in the floor that the vehicle picks up the signal produced by the wire and it follows that. The advantages to this system is that since there's no physical track, if there is people in the area that the robot travels, like in a warehouse, there's no trip hazard. Also, you can have multiple paths without having any mechanical track switches. The technology actually has been implemented since the 70s and it's still used today, although I believe newer systems are going away from this wire guidance system, and newer systems use a local positioning system, which is like a mini GPS system, or like the Amazon robots that Amazon bought out a robot company and started implementing it in their warehouses. They use QR labels and encoders on the robot to navigate the warehouse. Although, ever since Amazon released that video showing off their robot system, and really it wasn't their robot system, they bought out the company that designed it, I haven't heard any more of it. Usually demo videos of technologies like that are only demo videos, and usually there's problems that they don't admit in the videos that make the system not as good as it might seem. But that's just me being pessimistic. So a little backstory on why I built this robot. I got started into electronics back when I was in middle school. Somehow I stumbled upon robotroom.com and I just got real interested in it. This was back before YouTube. Robotroom.com is run by David Cook, and he shows off electronics projects he does and robots that he builds. And he actually produced the book Robot Building for Beginners, and I convinced my mom to buy me the book. And in the book you start from knowing nothing about electronics to building a line following robot, which is a robot that follows the line optically on the floor. Now in practice, in the industrial setting, they don't actually use line following robots because there's a lot of disadvantages to having a line on the floor. That line has to be clean. If the line's dirty, the robot could go off track. So the one thing I found interesting about inductive guided robots is that it's almost just like a line following robot that a lot of people do for their first electronics projects, but it's actually something that is used in real life. It's actually implemented in real life and used every day. So I got interested in building an inductive guided robot because I wanted to build something that could actually be used, for real. So let me go ahead and show you what I built. Now this circuit board is actually the circuit board that I printed. I made a video demoing how I print circuit boards, and I was actually printing off this circuit board. And this is the second inductive guided robot that I built. The first one worked, but it didn't work as good. There was new things I learned after building the first one. And originally I was just going to build another brand new one from scratch. But I had problems with the motors coming in from China, they got held at customs and I never got them in, so I ended up tearing that one apart and reusing the parts for this board. The heart of this inductive guided robot is this Atmel 328P microcontroller. It is the microcontroller that is used in Arduino, although I personally shy away from Arduino and I program it in AVRC. This chip right here is the L293D, and it is wired in as a H-bridge motor controller, and it's wired in to control the two motors, and it can control them forwards and backwards. Although in this implication, man, I'm stumbling on trying to say that word right. In this situation, the robot never travels backwards, but I had extra pins on the microcontroller, so I wired it up that way. We have a LCD screen, and underneath the LCD screen we have a 7805 5 voltage regulator. I originally designed the robot to run off of 9 volt rechargeable nickel metal halide batteries, and it would run about 10 minutes off of a battery. But in later years, after I got into quadcopters, I started using LiPo batteries. So I made this adapter to plug in a 3S LiPo battery into it. And that worked fine, except I eventually blew out this motor controller chip. I let the black magic smoke out of it. But it ran for quite a while before that happened. But it was never designed to run that high voltage battery, and I had problems of it going too fast. Now that's something that I could have changed in software, go back and change it. So basically when I put the LiPo in, it was pulling wheelies. When it would start, it would just do a wheelie and then it would go off track because the sensors would come off the ground. But I could always change that in software by having it accelerate, ramp up to speed. And also I can change software, the actual speed, to slow it down so it stays on track better. But I guess I was kind of lazy to get into that. And then, but once I got the thing running, I would have to kind of like hold up the back and let it skim. And then finally it would pick up traction. Once I got it running, it would stay on track. Real quick, I'm going to go and flip to the bottom side here. These two blue things are inductors, and I'm using them as a sensor to pick up the wire in the floor. And it has two sensors, and it takes in those signals and basically splits the difference. So the wire rides in between the two sensors, and it splits the difference between the signal strength to determine where the wire is located between the two sensors, and it corrects that to keep the wire as close as possible in the middle. And while we're looking underneath, these motor, gearbox, and wheel and hub assemblies, I bought all one piece from eBay, which just shows you the difference a little bit of time makes when the sandwich line following robot that you build using Dave Cook's system. Dave Cook's book came out. eBay never sold wheel and hub assemblies, and Dave Cook goes and uses Legos and super glues, makes a Lego hub to work off of gear motors. But nowadays, robotics have become so popular that you can buy full assemblies off of eBay. And then, of course, we have the power switch, and it drives off of these two wheels and it's differential steering, so it just varies the speed of each motor to turn. And I have this little wire harness clip used as a point to keep the front off the ground, and that actually works fine. It slides, you know, instead of having like a ball bearing. And as you can see, it wears out, but there's very little friction, so it actually works pretty good. This switch on the back is a I messed up moment, and I'll explain that a little later. And we have two bumpers. Let me get a better view here. We have two bumpers in the front of the vehicle so that if the vehicle hits something, it stops. Now the top of the board here is an op-amp circuit for the two signals coming in, and there's two stages to that. It amplifies the signal, and then it runs it through a peak detector circuit, and then finally it gets fed into the microcontroller. I put in a reset button for the microcontroller, and I put two user buttons to navigate the menu of the microcontroller. And over here is a row of capacitors that's used to tune the inductors into the signal. So it uses a LC bandpass circuit to tune the inductors into the signal coming out of the wire so it can reject other frequencies. And this switch here is used to switch in and out the capacitors. Now that mess up moment that I was explaining earlier is I thought that I could have one switch for both the left and right signals to switch in and out the same capacitors to tie them to ground. And that works fine if they're tied to ground. If the switch is off and it's not tied to ground, the two capacitors basically AC couple the two sides of the signal together, and we get the same signal in the microcontroller. So I printed this circuit board, not realizing that till after the fact, and I had to put in another dip switch in the back, cut traces. I believe I was able to do this, but I was able to solder on to the cut traces to add another dip switch. So each dip switch bank controls one side of the sensor switching in and out of the capacitors. And the reason I'm switching in and out of capacitors is to be able to select different frequencies so the vehicle can follow different paths if you create a situation where there's multiple frequencies for multiple tracks. And there's this vehicle can follow 4 different paths. So basically, if you want to follow, and you have to keep the dip switches in sync for both sides of the signal. So basically, right now, this one's set up to follow the first path, and this one has to be set up the same. So this one is set up, dip switch 1 is on. And that's basically an overview of the whole robot. I'm going to go ahead and switch out this motor driver chip, and we'll power it up. I do have a IC remover, but since this is such a small chip, only has 16 pins, I believe. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Yep, 16 pin dip chip. I can do it with a screwdriver, and luckily I socketed it, so when I blew out the motor driver, it's not a big deal. I just swap it out. Let me zoom in here to show you the top of this chip. Basically, when it blew out, like I said, I had it running off the LiPo battery, and it was running fine. And basically, when it went off track and went in a circle and went off track, and I have it set up so that if it loses the signal, the robot stops. It goes off track, so that way if it goes off the wire, it actually stops and doesn't go haywire. So it went off track, and I'm like, well, that's kind of weird because this thing works rock solid. It'll stay on track. I mean, it worked great. So when it went off track, I was like, that's kind of weird. And then as soon as I thought that to myself, like, oh, that's kind of weird that it went off track, the black magic smoke came out of it. And as you can see, the case is cracked right here. Now, theoretically, I assumed that it could handle the 12 volts of the LiPo. So then, after it smoked, I went back and did my calculation again, and my theoretical calculations of the motor draw still tell me that a 12 volt LiPo shouldn't have any problem. But I guess it ran for a good 20 minutes. I was running it a long time, because with that LiPo, like I said, with the 9 volt rechargeable battery, I could only get 10 minutes of runtime. With that LiPo, it just wanted to keep on running. So I guess just over time with the LiPo, the chip runs a lot hotter. It might need a heat sink with the LiPo. But the cool thing is that, like I said, I put a socket in, and you can get these motor driver chips. I forget what their official name is. It's a L293D. You can get them off of eBay relatively cheap. And there we go. We're ready to power up. Okay, we're ready to power it up. I have this 3S LiPo battery, and this time I only charged it to storage voltage so that it doesn't get full voltage, because this is more adequate enough for the power. Like I said, this robot was only designed for a 9 volt battery, and here's a 9 volt battery holder I put in the back. And as you can see, this LiPo fits in just fine. So I plug in this adapter that I made for the barrel connector. Let me see, switch. I don't know if the switch is off or on, we'll find out. This is the first time I powered this up in close to a year. Haven't ran it for over a year. It was August last year that I ran it last. Let's plug it in. And the power switch is on, and the LCD comes on. So the power switch is on the side here. Power switch comes on. So reset just resets the microcontroller. Then you have a menu here. You have the sensors, which gives you the analog to digital converted value of the sensor, and I'm only using 8-bit ADC because that was adequate for my application, and it makes things a lot easier than using 12-bit. And off the top of my head, I assume that it's ADCs are 8-bit and 12-bit. I don't think it's 16-bit, but I'm sure someone's going to correct me in the comments. It's been a while since I messed with ADCs on the Atmel microcontrollers. Now, when you're in this, so on each side, it gives you the signal value for each sensor, left and right. And in the middle is your calculated difference between the two sensors. That's what creates your error signal for the robot to correct its path. And because none of these components, the inductors and the capacitors, are precision components, there is a difference. There's a signal strength difference in each sensor for each track. So on this screen, if you press this bottom button, it zeroes out the difference. It makes an offset of the signal. So then that way you can place this robot in the center of the wire and zero it out, and then that robot knows where the center of the wire is. If I didn't add this, because of the signal strength difference, it might cause the robot to ride on one side or the other. But doing this way, I can zero it out. If I hit menu again, it's a motor test. So we can, and if I hit the bottom button, it will test the motors. So we can do this to see if the motor driver works. So let me lift it up some. and both motors turn. Oh yeah, I forgot to mention I have indicator LEDs on the bottom here. And then if you menu again, you go to this screen, which if you hit enter when you're on this screen, it starts the robot. Now, what happened was it started the robot, it saw it didn't have a signal, and it went off track. Normally, it would display off track, and normally it would, but I have a lot of noise issues with the LCD and the motors, just the way the board's designed. So constantly, I have to reinitialize the LCD in order to get the LCD to work, because once you start the robot and you try to output to the LCD, it just outputs garbage. So once the motor shut off, I reinitialize the LCD and then output stuff. Now, since the motor's starting to stop it real quick, the LCD didn't like that, so it never reinitialized right. And as you can see, it didn't reinitialize right. So every time you hit reset, the LCD still has power, but it sends a reinitialization. And as you can see, it just doesn't like that. So we're gonna have to power cycle it. And then give it a try again. And it doesn't work. Maybe when I set this up, I can show you that it does tell you, at this point, it's supposed to say off track. So, and you can start it again and again. Oh, there it goes. Finally, it worked right. So it's off track. So that prevents the robot from going crazy if it loses the wire. Okay, so the basic principle of how this works is the right-hand rule for conductors. Basically, the right-hand rule for conductors states that as you have current flowing through a conductor, a spherical magnetic field will be generated around the center of the conductor. So just like this. So basically, this is our signal wire, and this wire has AC current going through it at a specific frequency. So the current is actually flipping back and forth. But as the current is flipping back and forth, a magnetic field is being expanded and contracted going around the conductor, like this. And what the robot does is the inductor sensor on the robot. So here's the wire that's going to be embedded in the floor. And this is the wire here. That magnetic field that's being expanded and contracted, AC current, an alternating magnetic field, is going around the wire like this, with the lines of flux, I believe is the magnetic lines of flux, I believe is the right terminology. If it's not, people in the comments will probably be tearing me up. So that right-hand rule for conductors is like this. The magnetic lines of flux is going horizontally. So what we do is the inductor that we are using as a sensor, we put the inductor, turn it 90 degrees so that the conductors on the inductor is being penetrated with the magnetic field perpendicularly, because a magnetic field induces current in a conductor perpendicular 90 degrees away from the direction of the conductor for max inductive coupling. And then that's how the inductor picks up the signal on the wire. So if we bring the robot back out, and we have the wire that's the center signals being generated through going in between the vehicle. So we turn it on, and if I go to sensors, as you can see, each sensor is picking up a signal, and then this is the difference between the two. So it's in the middle, and actually the signal is pretty close to zero, but we're going to go ahead and zero that signal. So I'm going to press that, and it zeroed the signal. So now, as you can see, this is the difference between the two signals. So as the robot travels away from the center of the wire, as you can see, the signal strength on this sensor increases, and this one decreases, and our error signal increases in one direction. And you see how it increased to 76? So it's going to take that information and then change its steering to go back on course. And likewise, if we go the other direction, the signal strength increases in this inductor, and decreases in this one, and our error signal is negative. So now the robot knows that it needs to change its path to steer closer on this side. And then, so now if we go back to starting it, I'm going to lift up the rear wheels, and we hit start. The robot is driving. And as I go towards one way, it's going to slow down one motor. But of course it's going too fast, you can't tell. But it is changing the speeds of the motors. And if I take away the signal, it knows that the signal has been taken away, and it stops and goes off track. Okay, before we take it outside, I figured I would show you the 3 stages of the signal coming into the robot. So right now I have the oscilloscope hooked up to the first stage, which is the LC bandpass filter. All it is the inductor, which is this blue inductor that's actually picking up the signal, and it's a capacitor in parallel, and that creates a LC bandpass circuit, and that is tuned so that the resonant frequency is the frequency that's on the wire. So right here, the oscilloscope is hooked up just directly across the inductor. And as you can see, as I lift the robot away, the signal collapses. And as the inductor gets closer to the wire, the signal increases. So as it goes back and forth, the signal strength is varying based on how close that inductor is to the wire. Now, as you can notice, I have the oscilloscope hooked up to the channel 1 volts per division is 10 millivolts per division. So this is a very weak signal. In reality, it's like, oh, I lost my sync. The microcontroller can't do anything with this signal because it's just very low. So we need to put it through, and this signal is AC. As you can see, the ground isn't on the center. The signal is AC coming in. So the microcontroller can't do anything with that. So the next stage that it goes through is it gets amplified and rectified. And all I'm doing is putting it through an op amp. And my op amp is does not have a dual voltage source, dual polarity source. It just has 5 volts going to the source. So the op amp will automatically, since it doesn't have a dual polarity source, it will automatically rectify the signal and it'll amplify it. So if I take my oscilloscope and I put it to the output of the op amp, which is right here, as you can see, I gotta reset it. As you can see, there's no negative. But if we zoom out, so now we have a much stronger signal. I'm at 1 volts per division. So 1, 2. So our peak is at 2 volts. Oh, let me change this so we get locked in. And as you can see, it's rectified. So this is a half bridge rectifier. And it's just naturally doing that since the op amp doesn't have bipolar power source. So as you can see, all we have is that we have a DC signal that's amplified But really the microcontroller can't do anything with this because the signal is just ramping up and ramping down, and then we have half of it is at 0. So the microcontroller still can't do anything with it. So the third phase that it's going through is a peak detector circuit. Now you can just, what I did was I just Google searched different peak detector circuits, and there's actually a peak detector circuit that uses an op amp. So I went and I used the other side of the same op amp to do the peak detector circuit. Hopefully I can get latched on here. I think I'm latched on, I don't think I'm touching. So let's get the oscilloscope set. Nope, I don't think that's the right. Let me try going on the microcontroller. Okay, there we go. Okay, so now we're probing the output of the peak detector circuit. And basically, what a peak detector circuit is a RC circuit that is being sourced by the half-bridge rectified signal. And that's charging up the RC circuit. And then the RC circuit is also constantly discharging at a rate through the resistor. So you got to find the right equilibrium of discharge for whatever source you have, and it creates a nice steady DC signal based on the height of the peak. So as you can see, our ground's in the center of the screen. So as you can see, as I get closer to the wire, oh, maybe we need to move the ground down. Okay, we'll move the ground. The ground's at the bottom of the screen. So as you can see, as I get closer to the wire, the DC signal increases. As I get away from the wire, it decreases. Increase, decrease. And then finally, this is a signal that our microcontroller, the analog digital converter on the microcontroller, can read. And so that's how I'm picking up the signal. So now that I showed you that, let's go ahead and take this outside on the track and watch it run around. Okay, so I set up a track out here, and I had to go and change the settings in the robot because the settings I had it dialed in perfectly in the previous track that I used to run it at, but I can't run it there anymore. So I had to go and change those settings to adjust for this tight curve. And also, I was having problems that this cement isn't perfectly smooth, and with the wire in the way, it was interfering with the travel, so I put a cardboard on the bottom. But it still does work. It just doesn't, I really had it tuned in right where I used to run it. It would be nice and smooth on the wire. It doesn't do that anymore. I also slowed it down when I was in the code. I went ahead and slowed it down to adjust for the LiPo battery. So we just sit it on the wire and press go. And there it goes. Okay, I hope you found this video interesting and informative. There's other videos on inductive guidance on YouTube, but no one really went into in depth on how they did it, so I thought I would go ahead and make this video. And it was a neat project. I could definitely improve on it more. One guy on YouTube modify the RC car to work on the wire. And the RC car, the serving stereo, made it extremely smooth. And like I said, if I had the time to dial in the settings, I could make it go a lot smoother on this track with these tighter radiuses. So thanks for watching.